So the control for robotic platforms using trajectory optimization. In the past, a lot of robotics was focused on wheeled robots as they are more stable, they're easier to control, and they're just in general easier to use. But with us as humans, ever-growing need for robots that are able to do more stuff has come the need of legged robotics because they are more agile, they're capable of traveling more robust terrain, and they're just in general, they have access to more locations. So a way of controlling these robots is through the use of trajectory optimization, because it allows for an optimal and robust controller design that allows the robot to perform in different situations. Some background on trajectory optimization: it's just a bunch of mathematical techniques. It aims to minimize a measurement of performance known as a cost function, and it uses bounds and constraints that implement the equations of motion for the robot, with the main constraint being the equation of motion. So since this is a very mathematical thing, I'll skim over the math to not bore everyone. But basically, trajectory optimization uses the main constraint that's a manipulated equation as shown. This constraint just maps all the forces and masses of the robot to its coordinates. It then implies this equation as constraint in the optimization problem, and then balance the search space available so that the robot doesn't go into unfeasible states as to break itself. The constraint is criteria that needs to be met in order for the problem to be solved successfully. And since computers struggle solving real-time problems, this problem is broken up into discrete time using nodes, almost like how analog to digital signals are sampled. The solution then provided by this optimization is the path the robot needs to follow in order to reach a desired goal. For example, traveling 1 meter, and the path is then a discrete trajectory. So some extra techniques used to allow the generated path to be smoother, since it's a bunch of nodes as shown as I on the screen, is to use collocation. This just basically breaks up the path into 3 smaller points, as increasing the node points of the robot makes it longer to solve. And this technique has been shown successful in studies to keep nodes low while increasing the accuracy of robots. Some extra constraints are then applied into the actual optimization problem to allow for the points to match up to where they should be on the actual path of the robot. Another thing about trajectory optimization, it's very difficult to generate a full path, meaning acceleration, the steady state of the robot, as well as deceleration. To do this, the trajectory is usually split up into acceleration, steady state, and deceleration. Constraints are then placed on the path of the robot so that the acceleration phase ends where the steady state should start, and the deceleration starts where the steady state ends. This also allows you to optimize for different terrain, for example, a rough terrain with rocky road, a smooth terrain, and this allows you basically to create a library of different trajectories that allows the robot to perform in different situations, making it a very robust and agile solution for the actual robot. Another thing about trajectory optimization, there's a lot of constraints that are known as complementary constraints. These constraints basically have the form of alpha times b should equal 0. This is very difficult to solve since the solver struggles to get precise values. So a technique is employed known as epsilon relaxation. This is basically takes the 2 parameters alpha and beta and say they should be larger than a value epsilon. This epsilon is usually set to a large value initially, for example, 1,000. So this constraint is not solved as strictly, and every time a solution is reached, that solution is then used to solve again. This allows the solver to have initial problems, and then eventually you solve it enough times until you get as close to 0 as you feasibly can in the solution. Another thing in the optimization is the robot does not technically know what gravity is or when it touches the ground. So you basically code contacts into it. This is done in this case having lambda z times phi should equal 0. So this basically says if the foot is in the air, the forces on the on the ground should be 0, and if the foot's on the ground, the height of the foot should be 0, and vice versa. So now, since we're all doing software, let me show you some nice code of how it actually looks when you implement this trajectory optimization problem. Just a few seconds for this to load. So basically, this was done in Python's Jupyter notebook. You use SymPy basically to create a model. Everyone knows what NumPy is, and Biomer is just a solver. So yeah, you set up the model, setting like leg lengths and everything like that. Yes, all the constraints needed. And eventually, this is the equation of motions. Eventually, you go through the entire process of setting constraints, solving the manipulator equation, setting up gravity, setting up samples, the collocation I mentioned, everything like that. And eventually, when this thing solves like 8 times, you would reach a solution. For example, you can, since the solution basically provides everything you need, it provides like you can get the damping force on like a robot, you can get leg length at certain stops, you can get the force applied, you can get the leg position and velocity, and you can also plot different values. So this allows you to actually map it to a robot and its motors and successfully apply that to an actual robot. So now that the code is done and some of the solutions are shown, here's what you can do with it in animation. This is basically just showing the velocity of the robot and how it like runs over the ground. The solution is provided by the optimization. And yeah, now you can basically use this results and apply it to robots. How would you use that? Since this trajectory generated is discrete and does not map to an actual robot, you use linear interpolation. This is just a mathematical function that estimates additional information between nodes. You would then also use sensors as feedback, and then you can design a simple feedback controller. This is just known as a PID controller. Basically, what it does is it takes the state of the robot and then tries to sense into the future and also into the past, and then tries to control via that. How this would look on a robot can be shown as follows. This was applied to a UCT's PhD student's robot. And this is just an example of hopping. This robot was just constrained because hopping robots are very difficult if you don't have very expensive motors. So yeah, that's basically the use of trajectory optimization. And it's a very powerful technique to actually control robots, since controlling robots is the most difficult part of that. So yeah, thank you everyone for listening to me.